Thank you very much, David Holcomb-san. Yes, actually, just my experience, I was invited to the Nuclear Renaissance 2005 from Japan as just one person from Japan. And since then, I was working, of course, about 40 years for nuclear, but I should say that we had in Japan very big accident in 2011, 3.11. And what I'm talking now here is based on this kind of this experience in Japan. And also when I was in 2005, we had a discussion about nuclear proliferation of the nuclear bomb. And Japan is also experienced a nuclear bomb, still only one country. I don't want to be next one in somewhere, but anyway. So the Molten-Salt reactor was, okay, I should start the presentation, sorry. Yes, anyway, I'm presenting this with Furukawa, but this document was made by our groups, so just we are presenting. So we have introduction, and these other 4 items, transient analysis to the experiment, is just overview and give not including everything of Japan. So still, I have to say that. And okay, firstly, just introducing our activity in Japan, we have the non-proliferation organization called International Thorium Molten-Salt Forum, which is 2008 established by Professor Kazuo Furukawa for MSR technology. And this forum is, as David Holcomb said, as a kind of representative of Japanese, but just observer position, and continue to contribute to the chief MSR. And the other company, Thorium Tech Solution, which is called TTS, normally, is established 2010, which was just before the 2011. And this is the business private company. And so as I told you, we had this accident, and Professor Kazuo Furukawa made a very strong decision to develop the Molten-Salt reactor for real reactor. And the TTS was working very hard to do that. And now I can show you this TTS and items. These are both established by Professor Furukawa. And fortunately, from 2019, we got government support for 2 years. And we have three companies. Two of them are fluoride salt based on the MSRE technology, and the other one is fast neutron, reactor of chloride salt. But now I'm talking more about fluoride salt. And here, this Mostec is the new company I was establishing based on the academic work in Kyushu University. So these 3 are working together and still supported by the government. Okay. And now I have to talk about our history in Japan for the Molten-Salt reactor, because the Fuji is the name of the design, and so it was based on the Oak Ridge MSRE, and there are 4 items just to the first one is, this is a small size, which is based on the MSRE, but scale up to the about 1/5 of the large standard light water reactor. And we took out the online chemistry because we wanted to make it simple and to make it more easy to distribute in the many places. And we had the graphite-based neutron analysis with thorium.
Yeah, it looks like there's going to be. I'm going to be busy.
Then we got the conversion ratio 1.0, and which means we can sustain the reaction.
Week.
And also we didn't want to replace the graphite during the whole lifetime. So we used the low neutron fluence and took 30 years operation. But this is a question. There are questions about material. But anyway, okay. We don't have enough time, so I have to speak a little bit faster. We have two books, which one is the Professor Doran's Molten-Salt reactor of thorium energy, and the other one is the IAEA document. So my talk is quite much written in this book. Okay. And this is the just overview of the Molten-Salt activity, and just talk about the Fuji is the offline, and in the right-hand side you can see the bird, which is Japanese, and based on the almost academic, but recently we got the participation of CRIEPI, the Japanese EPRI, which was specialized for the chloride pilot processing together with Argonne National Laboratory. And so they went into this work in chloride salt, but also in the fluoride salt together with TTS. So that's a big change in this 1 or 2 years, yes. And this is the Fuji reactor, which I was talking. And as you can see, the central area, I mean, red one is the MSRE, but we just put the secondary circuit and the power unit. And so it was designed in 1990. So it's an old concept. So but presently our discussion or the working is quite based on this old, I should say old, but 1990s basic. And so maybe we have to go forward. And this is another experimental work in Japan. The right-hand side is the fusion reactor facility. I mean, the blanket loop with Frynac. And the left one is the Sukegawa company, which is working this kind of blanket and loops and so on. And we have the graphite work for Toyo Tanso and so on. Maybe you know that. And we worked for the high temperature gas reactors, but also we are looking at to use this technology. And Hastelloy N was licensed to the Mitsubishi Metal. And so we have some samples and some kind of production still going in, yes. And we use, we were working together with Checo CVR for the reprocessing. And this is fluoride. We have a much more detailed the flow sheet for the fluoride reprocessing. But based from our design, we think about offline anyway. Okay. And one thing in Japan, we have special condition is that we do not, the government do not, or the people do not want to have the excess plutonium. Of course, plutonium is the energy source, but if we have more than the necessary, maybe it's not good. So politically and also technically, we want to reduce the plutonium amount. Here I'm showing the performance of the Fuji reactor to reduce the plutonium. Because of that is soft neutron, so the cross section is bigger. So but also because of the simple system and the Molten-Salt reactor performance, that is better than the light water reactor. Maybe I don't know. Okay, and we have several work for the software, and this is just transient analysis made by Professor Shimazu of Fukuoka University, Hokkaido and Fukuoka University. And we can manage to reproduce the MSR experiment quite well. Of course, that is, many people are doing that. And you can see, this is the Fuji reactor performance of the load following. And anyway, this is one example, but load following is easier if we can get out or take out all the xenon component, then we don't have the xenon transient problem or light water reactor. Okay, and we have the this kind of work written in the books, and so. For example, regulatory guide for reactor safety design and regulatory guide for the safety assessment. And these two are made based on the light water reactor licensing. And this was, and about proliferation resistance, this is very much interested concern, but I should say there are many remaining discussions, but the point is that we wanted to make it on the kind of discussion ground and we repeated maybe classical argument, but as you can see, the proliferation resistance is in many type problems. I mean issues, current or some kind of things. As a result, anyway, there is a potential resistance. Because of the uranium-233 gamma radiation. And the physical protection is the problem, but there is a IAEA discussion, and based on IAEA discussion, in the framework of IAEA discussion, we concluded that the MSR is appropriately protected against DPT. And we have the freeze valve experiment, which was conducted by Professor Okawa of the University Electrocommunications and his students. And but I just skip it because it's not so relevant. And also we had a freeze valve experiment. Unfortunately, we have delayed due to the corona, and because we couldn't go into the national laboratory in this case. But anyway, we have such kind of activity. Okay, thank you very much. Yes.